Hi class, Mr. Morris, and we're doing a video on Lewis diagrams. So some of you guys got really good at this. Some of you maybe it's a little rusty, so we want to go back and relearn how to do this. A covalent bond, as you know, is a nonmetal. And a nonmetal that share valence electrons. And we represent this with a line. So if there's electrons being shared, we represent it with a line. Lewis diagram is used to show how the electrons are being shared between atoms. And then we have the octet rule. All atoms want to achieve 8 valence electrons with a couple exceptions. Except for hydrogen, it wants 2 valence electrons. We could also mention here boron wants 6, and even though beryllium is actually a metal occasionally, it behaves like a nonmetal. So beryllium actually only wants 4 valence electrons. So just be aware of those. We're going to get into those in a moment anyway. Okay. A line represents bonded pair of electrons. So when we're drawing our Lewis structures, we typically don't do dots for shared electrons. We typically want to show a line to indicate that the electrons are bonded. And we do 2 dots to show a lone pair of electrons. That means that they're unshared. A skeletal structure is the word that we use to describe the arrangement of the elements. It tells who's in the middle, and they're connected by some bonds. Okay. The element that's first mentioned is almost always in the middle. Okay. If there's more than one, then they're also in the middle. And know that hydrogen is never in the middle. So we want just a little practice counting electrons. Remember, each dot represents an electron and each line represents 2 electrons. So if I were to count these, I would say this is 2, 4, 6, 8, 10, 12. That's 12 electrons here. And with this, I would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. By the way, either of these drawings is accurate, but the one at the top is preferred because it shows the electrons are bonded. They're being shared. Okay. Same thing with this next one. We could count the electrons 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, and then each bond is 2, so that's 5, 6, 7, 8. So we've got 8 valence electrons being shown in that diagram. Okay, HCN, we have 2, 4, 6, 8, 9, 10. So I've got 10 valence electrons. 2, 4, 6, 8, 10, 11, 12, 13, 14 in that diagram. All right. And then we have our bonds up here. Different types of bonds we could have. We've got a single bond, which is represented by one line. That's 2 electrons being shared. A double bond, we have 2 bonds, so 4 electrons are being shared. A triple bond is 3 lines, 3 bonds, which is 6 electrons being shared. Each line represents 2 electrons. Here are our rules for drawing Lewis structures. And I'm going to kind of summarize in a word, just a way to remember what this is, what each rule is talking about. So count the total number of valence electrons available. We want to pay attention to the overall charge. It's the negative ion. If it's a negative ion, so we're not talking just a neutral compound. If you actually have a polyatomic ion and it's a negative ion, you have more electrons or extra electrons. A positive ion has fewer electrons or less electrons. Okay, fewer is probably more grammatically correct, but we'll have fewer electrons. All right, so for this, we want to write the word available. Before we can even get started, we need to know how many electrons we have available. So you look at the column that it's in to decide how many valence electrons it is for each element that comes. So if you've got carbon, it would be 4. If you've got oxygen, it would be 6. And you add those up to find out the total number of electrons available to work with. Then we're going to place the singleton atom in the center. So that's how we decide which one goes in the middle. It's usually the first element in the formula. And we use one pair of electrons to bond each outer atom to the central atom. Okay. These two together, these steps together, make up the skeleton of the Lewis dot structure. So putting those two steps together, we're just making the skeleton of the Lewis dot structure. And then step 3, we want to complete the octets of the outer atoms, right? Outsiders. We're going to make the outsiders happy first. Always make the outsiders happy first. And if, that's a big if there are extra electron pairs, you place the remaining electron pairs on the central atom. This is what you do with the leftovers. So step 4 is just talking about the leftovers. If you have any, then we're going to place the extras on the central atom. This is particularly useful if the central atom is from periods 3 to 7, because that means they can have more than an octet. Sometimes, because they have these d orbitals, they can have an expanded octet, so you can have an atom in the middle that has more than 8 valence electrons around it, which is really strange, but it can happen. If there are not enough electron pairs to give the central atom an octet, we're going to make double or triple bonds. And this really only applies to C, N, O, P, and S. Carbon, nitrogen, oxygen, phosphorus, and sulfur. So you can remember that with the kind of the acronym CNOPS. CNOPS. Okay. And I always just say that these last 2 steps, what we're really trying to do is just check and see if everybody's happy. Just ask that question. Is everyone happy? Or at least as happy as they can be. That's our goal. Remember, they want to have 8 valence electrons except for hydrogen, beryllium, and boron. Remember, hydrogen wants 2, beryllium wants 4, and boron wants 6. Those are the only ones that don't want 8. And finally, if it's a polyatomic ion, you want to put it in brackets. So let's do some example problems. I want to do a couple of these that the structure is already drawn for you. So this has already taken care of this step 2A, the skeleton. The only thing we need to do is connect them with electrons. So we're going to do steps 1, 2B, 3, and so on. You always have to start with the math. There's a lot of students who try to skip this step, and they very frequently make mistakes. So you always start with the math. Chlorine is in group 17, so that means it's got 7 valence electrons, and since I have 2 of them, I'm going to do 7 times 2. It gives me 14 valence electrons. That's what's available. So that's step 1, or available. I've got 14 valence electrons. Okay, step 2, I need to make sure that I've got my skeleton drawn, and I'm going to connect them with one bond, just a single bond. After that, I look at the outsiders. Well, in this case, they're both outsiders, so we're going to try to make both of them happy if we can. So we've got only 14 electrons to work with. I just used 2 of them. I'm going to keep going. That was 2. I've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's all of my electrons. Now let's look at our steps up here. So I've got my available skeleton. I made my outsiders happy, or I used all of my electrons up. Now we just want to check, do we have any leftovers? We don't. We used every electron. Now we just need to check if they're happy. Does everybody have the number of electrons at once? Well, chlorine is not an exception. It's a normal atom that would like to have 8 valence electrons around it. So we have 2 in the central bond, 3, 4, 5, 6, 7, 8 on the left side, and then on the right side I've got 2 because of the bond, 3, 4, 5, 6, 7, 8. So both chlorine atoms are surrounded by 8 valence electrons. We're done. Okay, with oxygen. Oxygen is in group 16, so it has 6 valence electrons. Since there are 2 of them, we multiply by 2, and I get 12 valence electrons. That's what's available. Now I want to check my outsiders, or first connect the bond. We go to skeleton, connect it with 1 bond, and then we want to try to make the outsiders happy. But remember, when you run out of electrons, you're done. Okay, so I just used 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I used 12 electrons. I've run out. Now let's go back up and check everything. I definitely don't have any leftovers. So we did available, the skeleton, our outsiders are happy, or we tried to make them happy. We don't have any leftovers. Now this is when we check if they're happy. So step 5, if there are not enough electron pairs, we're going to give double bonds. So let's see, I've got 2, 4, 6, 8. That's enough to make the one on the left happy. But on the right, I have 1, 2, 3, 4, 5, 6. I don't have enough electrons to make both of them happy. So this is when I would take 2 electrons from the atom that is already satisfied, and instead of it having those electrons all to itself, it's going to share them. Move it down, and we're going to form a double bond. And we still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You've still got the same number of electrons, but now if you look at how they're being shared, we've got 1, 2, 3, 4 because of the bonds, 5, 6, 7, 8 on the left, and then on the right, 1, 2, 3, 4 because of the bonds, 5, 6, 7, 8 on the right. So now they are both satisfied. This is the final Lewis structure that we're going to be using. Okay, finally we look at CCl4, and then after this one I'm going to pause the video, give you guys some time to work through some example problems and come back and check your work. Okay, so number 4, again, we want to count, we want to do the available, skeleton, outsiders, leftovers, and then check if they're happy. So CCl4, first let's do our count. Carbon has 4, plus chlorine has 7 multiplied by 4. So I end up with 28 plus 4 is 32. Start with 1 bond to each of the outside elements. 1, 2, 3, 4, which is 2, 4, 6, 8 electrons. And then we want to make our outsiders happy first. So I have 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And if you look at it, each side has 2 electrons on it. So we have 2, 4, 6, 8, 2, 4, 6, 8 for the bottom chlorine, 2, 4, 6, 8 for the chlorine on the left, 2, 4, 6, 8 for the chlorine at the top. And for carbon in the middle, those bonds, I've got 2, 4, 6, 8. So carbon's happy. Everyone is happy. And we're done. We can always go back and double check, but we checked our available. That's the math. We made the skeleton. We made the outsiders happy. We did not have any leftover electrons because we used them all up. And then they all have 8 valence electrons. So all of the atoms involved are happy. And we're done. I'm going to stop the video here and do some example problems on the next one.